Hello, class. So today we are going to talk about causal inference, and in particular, we're going to talk about randomization and how it helps us with causal inference. These are the packages that were used to make these slides. So let us start at the top with why we want to do impact analysis to begin with. Our job as economists is often to reveal linkages. If we want to inform policy decisions or business decisions, often the question is, if we do A, will we get B? If we try to make forecasts, then the question might be, if we see A at time t, what can we expect about A at time t plus 1? So doing both of these depends on our ability to reveal linkages between the variables. Those linkages can be thought of as correlations or as causal linkages. And ultimately, the holy grail for us is to reveal the causal linkages. Revealing causality is often the ultimate goal for us, and the vast majority of applied micro is about revealing these causal links. Most of the econometrics that we've learned in grad school are geared towards that, either just to showing that a causal link exists with a significant beta, or trying to measure the size of that causal link, looking at the magnitude of beta. As an aside, machine learning feels a little bit awkward to economists right now, precisely because of that reason. We've been thinking about the causal link for so long that now it's a little awkward for us to be thinking about correlations. But we'll talk about machine learning later. This is not the topic for today. So you can think of there being three core questions when you're starting a research project in applied microecon. The first one is, what is the causal relationship of interest you're trying to look at? The second one is, in an ideal world, what would be the experiment that we would do to test this causal relationship? Most of the time, this ideal world does not exist, and so you need to think about what will be your identification strategy. The identification strategy being, how am I going to use data to approximate this ideal experiment that I would have liked to make? Another way of phrasing the identification question is, can I find some exogenous variation that will help me test this causal relationship of interest? So before we get into, let us first understand why a randomized experiment is the ideal situation. So in a regular hard science lab, you can have a perfectly controlled experiment. For instance, if you look at this picture, you have an experimental group with pots that receive water and a control group with pots that do not receive water. Then, after a few days, some of the pots have sprouts, others do not. And so, in this situation, the difference between the number of seeds that sprouted in the water treatment and the number of seeds that sprouted in the no water treatment is 100% caused by that treatment. So delta sprout, we can call it, is 100% a causal impact of the treatment. This is, of course, unless there are any confounders. One possible confounder could be, for instance, if some pots were left in the sun and other pots were left in the shade. This would confound the experiment. However, in a lab, we can make sure that this isn't happening. Another confounder could be if, for instance, the seeds in the water treatment were different from the seeds in the no water treatment. And the way we avoid that is by taking the seeds from the same batch. Underlying that is the assumption that the seeds are all comparable, and one way we do that is by drawing them from the same package. That is, in essence, an assumption of randomness. The randomness issue becomes more explicit if we're thinking about drug testing. Imagine you have a population of sick people that is divided into two groups randomly. One group gets an intervention and the other one does not. Then, at the end of the trial, if there's a difference between the number of sick people in the intervention group and in the control group, we can assume that that difference is 100% caused by the treatment. This is because we randomized allocation into the two groups. This interpretation breaks down if the randomization was not done properly. Now you can take that exact same slide and think about it as an economics experiment. Instead of imagining this as a drug treatment, let us think about this as a back-to-work program. We have the exact same setup. If the back-to-work program was properly randomized in its allocation, then the difference in employed people in the intervention group and in the control group can be thought of as having been caused 100% by that treatment. Again, however, this relies on the assumption of randomness, meaning that the probability of having entered the intervention group or the control group is completely independent from any other characteristic. If the randomization has failed, then we cannot explain this difference in employment as having been caused by the treatment. Now, science labs are not immune to the problems that we face as economists. However, for us, they may be a little more likely. Why is that? Because the way our programs are implemented. Economics programs tend to be implemented by clusters, let's say in a given city or in a given neighborhood. This tends to make randomization less than perfect. In addition, we have very little ability to control what is going on with our sample. Economists may face additional problems with the econometrics and statistics that we're trying to run on our data, because economic variables might be a little more subject to measurement error, and because our experiments tend to be costly and difficult to implement, so unlike in a science lab, we can't just rinse and repeat. Okay, so after this little introduction, we're going to look at the point of randomization in more formal terms, using a little bit of math. Let us take this example that is used in Angrist and Pishka's mostly harmless econometrics. Imagine you want to ask the question, does going to the hospital make people better? You want to solve this empirically, but if you do the most obvious thing to do, you're going to have a problem. Let's say you compare people who went to the hospital with people who did not. Here's some example data of what you find. People who went to the hospital have a health score of 3.21. People who did not have a health score of 3.93. Well, that looks like the people who went to the hospital are more sick than the people who didn't. So maybe the hospital makes them sick. Obviously, this is not the right conclusion. The problem is that there was selection in the people who went to the hospital versus those who did not. In other words, since only sick people go to the hospital, they self-select into receiving the hospital treatment. This is an exaggerated example of why we need randomization. Randomization is solving that kind of problem. Let us continue with this example and define some notation. Assume you have an outcome yi, let's say that is health of individual I, and a treatment dummy di, let's say it's having gone to the hospital or having not gone to the hospital. Formally, what we want is the effect of di equals 1 on yi. More specifically, we want to know how y compares to what it would have been if individual I had not gone to the hospital. So the problem here is that we are trying to compare something that happened to something that did not happen. We want to compare y after someone went to the hospital to the y they would have had if they had not gone. So let us use some notation for potential outcomes. Let's say that yi is either equal to y0i for di equals 0, no hospital, or y1i for di equals 1, hospital. Only one of those two will ever be observable. The other one is always a hypothetical. Either you went to the hospital or you didn't. We can conveniently rewrite this yi as yi is equal to y0i plus y1i minus y0i times di. If you replace di by its value, you can see that when di equals 1, then yi is equal to y1i, and when di equals 0, yi equals y0i. You should already notice that this di acts like a dummy variable in the regressions we usually run. Now this difference y1i minus y0i is the causal effect. Let's talk about it a little more. So what we want to measure is y1i minus y0i. It means the health status if you went to the hospital minus the health status if you did not for the same individual I. That is the effect of the hospital. But again, only one of those is observed. This causal effect is either your health if you went to the hospital minus what it would have been if you had not, or the potential health you would have if you went to the hospital minus your current health if you did not. And naturally, because it is impossible to actually observe both, what we need to do is take expected values, which we get from averaging across people. So the causal effect is the expected value of your health if you go to the hospital minus the expected value of your health if you don't. Now what we observe is the average impact or the expected value of health for those who went to the hospital minus that of those who did not. If we simply insert this term in red, first with a minus, then with a plus, we see what selection bias is. Here we have conveniently split this into two terms. The expected value of going to the hospital minus the expected value of having not gone to the hospital for those who actually did go. That is the average treatment effect on the treated. It is the difference between the average health of those who went minus what it would have been if they hadn't gone. But this leaves us with this second term, which is the difference between the outcome of having not gone to the hospital for those who did and those who did not go to the hospital. This is the selection bias. It captures the fact that those who did go to the hospital might have gone there for a reason. Because their y0i would have been different. So now we understand the problem. What we observe is the difference between those who went to the hospital and those who didn't go. But that embeds in it the average treatment on the treated and the selection bias, and those are hard to disentangle. We cannot disentangle them because we don't observe what would have happened to those who went to the hospital if they hadn't gone. So why does randomization actually solve that selection problem? Well, because randomization makes DI statistically independent from Y0I. Remember that in statistics, statistical independence between A and B means that the probability of B is equal to the probability of B given A. So because randomization gives us statistical independence between DI and Y0I, what it gives us is that the expected value of Y0 if you go to the hospital is equal to the expected value of Y0 if you don't. Now, since these two terms are equal, this bias is equal to 0. And then what we observe is the average treatment on the treated. Let us look at this graphically. On this axis we have time on the x and health on the y. The only thing we observe is this period. We don't know exactly what happened before. But let us imagine the people who did not go to the hospital had high health before. They have the same health now. Y0i given d equals 0 is this dot. The people who went to the hospital perhaps had bad health before. Then they went to the hospital and their health that we observe is now y1i given that d equals 1. These people went, these people did not. Our data that we observe is simply the difference between this and that. Here we see that the average treatment on the treated is actually the difference between what would have happened to those who went to the hospital if they hadn't, and what actually happened to them because they went to the hospital. However, that's obviously different than what we observe. Now, the selection bias is the difference between what the health would have been of those who did go to the hospital if they hadn't gone, and those who simply didn't go. This graph shows why, while the average treatment on the treated might be positive, the difference between this and that, what we see with our observed data is something negative, the difference between this and that. And this is entirely attributable to this selection bias. Now, what does randomization do for us? It gives us statistical independence between y and d, meaning that the y0 is equal for d equals 0 and for d equals 1. Now, if you bring this y0i given d equals 1 up to the same level here, then what you observe is the average treatment on the treated. The selection bias is 0. Naturally, this also means that we would have drawn our sample at random from a population with indistinguishable health status. Now, of course, this experiment of randomly sending people to the hospital would be costly and silly. However, it is a useful thought experiment that can help us think about how we should really go about figuring out the causal impact of something. Okay, so now that we've seen the theory, we're going to look a little bit at the practice of how we measure these impacts. So following what I just explained, in the perfect case where we have perfect randomization, all we need to do is take the difference in means. Remember that the causal effect is y1i minus y0i, and under perfect randomization, we can just take the expected values of y1 and y0. So that is simply the mean for those with treatment equal to 1 and the mean for those with treatment equal to 0. The lab experiment is a good example. In that case, you don't even need a regression to measure the impact. You just take the difference. So here's an example, which we're going to run as a simulation in R. Imagine you have a population with incomes distributed between 0 and 200. You decide to give $50 to half of that population. In order to randomize, we give it only to the people that have an even ID. And then we measure their income immediately after they've received the gift. Here you have some code that sets this up. This is the original Y, this is the dummy that defines who gets treated, and this is the Y after they get treated. We make this into a data frame. We take a look at what we have. This is the person's ID, this is the income we observe after the treatment, and this is the dummy. Note that we do not need to observe the income before the treatment, or we assume that we don't observe it. Our simulated data looks like this. The ID is on the x-axis, and the income after the treatment is on the y-axis. Clearly you see that the non-treated, in red, have lower incomes than the treated, in blue. And the minimal income for those who are treated is $50, which is the amount that we gave. So because we randomized this treatment, we can compute the impact of our treatment simply with a difference in means. So we calculate the mean for the treated and the mean for the non-treated, and the effect is the difference between the two. The mean income of the non-treated is 100 by definition. The mean income of the treated is 150, not surprising, and the difference is almost 50. These results are exactly what we would expect. Now, to show this difference in means, we run this code, which I'm not going to discuss, but you have it for the record. Here, the non-treated have these incomes, the treated have those incomes, and the difference in means is the difference between these two lines. Now in practice, we'll often look at this using a regression. How would that work? Remember that we wrote that yi is equal to y0i plus the causal effect times a treatment dummy. Now you should see how this resembles a regression. yi is equal to alpha, a constant, plus beta times the dummy. In this case, beta is the estimate of our causal impact. Naturally, epsilon I is the error. So the treatment effect regression should be interpreted as follows. Y, the income, is equal to alpha plus beta times d, meaning that when d is equal to 0, the expected value of y is alpha, so the intercept is the mean income of the untreated. And when di equals 1, the expected value of y is alpha plus beta, so alpha plus beta is the expected value of y for the treated. If we estimate a model using the linear model command in R, that simply regresses y post on the treatment dummy using our data, we look at the coefficients and we find that the intercept is 100.72 and the beta is 49.50. If you want to look at this in a more standard format, you can use the Stargazer package, which makes tables such as this one that you should be familiar with. But the point is that we've obtained the exact same results for the intercept and the beta as we did by calculating the difference in the means. So if we plot this data and the regression line using this code, we obtain this. Here are the incomes of the non-treated. Here are the incomes of the treated. And as you see, the regression line has the mean of the non-treated as an intercept and the treatment effect as its slope. So given that regressing on an intercept and the dummy gives us exactly the same result as taking the difference in means, why do we bother doing this with a regression? Well, because when we regress, we can tackle less than perfect randomization cases. So let us continue with this example, but now introduce some potential issues into the simulated data that we create. So now imagine that you have the same scenario. You are distributing cash to people randomly selected. However, now those people happen to live in 2 different cities. For logistical reasons, in the second city, you only select a quarter of the people to receive the randomly allocated transfer. And it so happens that that city has slightly lower incomes to begin with. So here is the code that simulates this. You have 2,000 people in each of the 2 cities, the second one having slightly lower incomes. And in the first city, every other person receives the transfer, while in the second city, every 4th person receives the transfer. Here is your data with incomes after the transfer, a dummy for the treated group, and this is a dummy for the city. The D dummy and the group are the same, just one of them is used as a factor, the other one is an integer. This is what the data look like. The people with IDs between 0 and 2000 are the first city. The ones with IDs above are the second city. Again, you see that the treatment group in blue has higher incomes, but in the second city, everybody has lower incomes in general. So now we do what we originally did. We just run a model of our income post-treatment on a treatment dummy, and we expect to get $50. This is, after all, the amount that we transferred to people. However, we can see that the treatment dummy gets a coefficient of 61. This is not what we expected. It's obviously wrong. How do we solve this? All we need to do is add a control variable for the city. Now we regress the incomes on the treatment dummy and control for the city, and the treatment dummy now has the correct coefficient of about 50. Now, how do we interpret each coefficient? Recall that dummy variables just shift the intercept. D is a dummy, city is also a dummy. So 98 is the intercept when D equals 0 and city equals 0. So this is the average income of the non-treated in the first city. D is our treatment effect, meaning that the treated group has incomes $50 higher than the non-treated group. And city shifts the intercept for everyone in the second city. On average, the second city has incomes lower by $38. So why does the city actually matter here? Mathematically, what is the problem? It's that the probability of getting the treatment is correlated with the city. And because y is also correlated with the city, this creates some endogeneity. If you enjoy running simulations, you can try to see what happens when only one of these problems happens. So now let's imagine a third scenario. Same as before, you're trying to distribute $50 to people randomly. In this case, we're back to just having one city. However, let's imagine you had 2 employees, and it so happens that one of them was corrupt and kept half of the cash. The honest employee had the first half of the sample, the second employee had the second half of the sample, which is still distributed at random. So here we construct some data to simulate this corruption scenario. You still have people with incomes between 0 and 200. The corrupt employee is distributing in the second half of the sample, and the treatment dummy still goes to every other person. So now in our data, we have the incomes after the treatment, the dummy for the treated and the non-treated, and the group, which tells us whether the honest employee or the corrupt employee gave you the treatment. So this is what our data looks like. Again, the non-treated group in red has incomes between 0 and 200, and the treated group in blue has incomes that are higher, but the first employee distributed $50 to people, while the second employee only distributed $25 and kept the rest. Now again, let's start with the naive regression. We expect to get $50 as an impact. We regress the income after the treatment on the dummy. Of course, we don't get the correct answer. How do we solve this? Well, the first answer might be we want to control for the group, and so we regress the outcome on our treatment dummy and the group, which is essentially an employee dummy. However, this is still not giving us the correct answer. D1 is 36, and the group dummy is 14. Why are we still getting something odd? Because what we need to add is the interaction term between the treatment dummy and the group dummy, right here. Once we account for the interaction term, the beta on our treatment dummy is 50, which is what we expected, and the beta on the interaction term is 25, which is the amount of money kept by the corrupt employee. Okay, so let's recap on how these coefficients are to be interpreted. In the model with the 2 cities, we have 2 terms, a dummy for the treatment and a dummy for the city. And in that case, the treatment effect is beta. However, unless we control for C, then beta will be biased, it will be incorrect. Now in the corruption model, we need to have 3 terms. We have the treatment dummy, we have the group dummy, and then we have the interaction between treatment and group, where the group defines whether or not you've been subject to corruption. And in this case, the interpretation is different. Beta 1 is not the overall treatment effect. It is the treatment effect in the first group only. If we want the treatment effect in the second group, we need to add beta 1 plus beta 3. In other words, in this case, we are actually estimating 2 regression lines, one for the first group, alpha plus beta 1 times d, and one for the second group, alpha plus beta 2 plus beta 1 plus beta 3 times d. Okay, so let us do a little wrap up of what we saw today. Well, first of all, notice that I haven't talked about the significance of coefficients at all. In addition, I didn't talk about how you can randomize at different levels, for instance, with clustered randomization. And finally, let me add that all of this that we did today We didn't even start talking about panel data. At this point, we only have end-line data, but it is important to realize that with true randomization, we don't actually require pre-treatment data. There are papers that have randomization and only post-treatment data. Nowadays, it's harder and harder to publish papers like that. Most of the time, you're going to need panel data to be convincing. Here's an example of a paper by Kruger in 1999. This article looks at the impact of class size on children's educational achievements. They do not have pre-treatment data. However, because the children were randomly assigned to their classes with post-treatment scores, they are able to obtain estimates. And finally, for further reading, I would recommend Mostly Harmless Econometrics by Angriston Pishka. Part of this lecture was inspired by the first chapter of that book.